Okay, so the next speaker is Krzysztof Sacha on time crystals.
Thank you very much, and thank you. I am grateful to the organizers for having me here. It is a great conference, and I enjoy a lot. I'm going to tell you about time crystals, but before I start, I would like to show you the list of people who have been involved in the research on time crystals, which we are doing in Krakow. There are many people. Two of them are in red. These are PhD students who are finishing their PhD, so they are good candidates for postdoc position. Okay, so the plan of my talk is first, I will tell you about how to create crystalline structure in time, somehow by hand. And then I switch to the spontaneous formation of time crystals, and at the end, I conclude paving some way towards timetronics. Crystalline structure in time. I have to start with reminding you what are classical resonances. Resonances have different meanings, but I really mean something very simple. But instead of showing you some mathematical formulas, I would like to present some experiment. What are resonances? The simplest resonance, this is a resonant motion. And this is actually one-to-one resonance, because the period of the ball motion is equal to the period of the bed motion. But if I move the bed twice faster, then I can realize two-to-one resonance, because then the period of the ball motion would be twice longer than the period of the bed motion. And actually, if I was a better tennis player, I am not, for two-to-one resonant driving, I could keep two balls on the two-to-one resonant orbit. Sorry. So this is a classical motion, classical resonant motion. But now let me switch to the quantum version, and let us consider, for example, atom bouncing on an harmonically oscillating atom mirror. And then it turns out that we can still find resonant states. And for example, when we have 4-to-1 resonance, the resonance states are represented by the superposition of 4 localized wave packets, which are bouncing off the mirror and which are moving along 4-to-1 resonant orbit. And these 4 localized wave packets are like these 4 ping-pong balls, which are moving along the 4-to-1 resonant, classical 4-to-1 resonant. But this is a plot of the resonance states for fixed moments of time, but in the plot in the configuration space. But the configuration space is not the domain where we can observe crystalline structure. Crystalline structure we can observe in the time domain, which means that when I fix position in space, I locate a detector close to the resonant orbit, and I ask how the probability of clicking of the detector, how it changes in time. And if we have resonant drive states, then we observe that this is periodic in time. And this is the domain where we can observe crystalline structure. And to make this conjecture more apparent, let us restrict ourselves in the description of our quantum particle, let us restrict ourselves to the Hilbert subspace, which is spanned by this localized wave packet, by the resonant states. In this subspace, the energy of the particle takes the form of the time-binding model, where we have a tunneling amplitude, and this tunneling amplitude describes tunneling of the particle between neighboring wave packets, but neighboring in the time domain. There is also longer range or longer time tunneling, but these are orders of magnitude weaker, similarly like it is in the typical condensed matter situation. So let me summarize this. What we have the classical resonant orbit. We are interested usually in the large resonant number. And along this resonant orbit, when we switch to quantum mechanics, we observe that our particle behaves in the same way like an electron in a condensed matter system. And we can do condensed matter because it depends on the number of resonance. If there are 4-to-1 resonance, then we have 4 localized wave packets here. And when you fix the position in space, you locate detector, for example, at this point. Then when each wave packet is coming, then you observe the highest probability. This is just like you focus on a single point, and then you are asking, what is the probability? How's the probability of detecting of a particle? How it changes in time? It will appear many times, so maybe it's clear. Okay, so let us consider some non-trivial phases. Anderson localization in the time domain. Of course, we know Anderson localization is a localization of a particle in the configuration space due to the disorder in space. Anderson localization can be also observed in the momentum space. Sometimes it is called dynamical localization. And then it is related to the quantum suppression of classical diffusion in the system which are classically chaotic. So yet another version of Anderson localization is possible, Anderson localization in time due to the disorder in time. So suppose that we have our harmonically oscillating mirror, but now let us turn on some weak perturbation. But this weak perturbation fluctuates in time. But we assume that it still fulfills periodic boundary conditions on a long time scale, on a time scale related to the period of the resonant orbit. And then the presence of this perturbation leads to the additional terms in our time-binding description. And these additional terms actually bring the disorder to the system. And this is nothing but Anderson model. And Anderson localization can be observed, meaning that if we fix the position in space, and we ask how the probability for clicking of the detector, how it changes in time, it becomes exponentially localized around a certain moment of time. And I think that this is a good moment to compare space and time crystals. Suppose that we have a one-dimensional space crystal with periodic boundary conditions. When we have disorder in the system, then we can observe Anderson localization, which means that when we go around the ring, we see that at a certain point, there is an exponential localization of the particle. Switching from space to time crystals, we have to exchange the role of time and space. Now we fix the position in space, and we are asking how the probability of detecting the system at this point, how it changes in time. If there is Anderson localization in time, then we observe exponential localization around a certain moment of time. And this behavior is repeated periodically due to the periodic boundary conditions in time. And it turns out that this Anderson localization in time is a pretty general phenomenon. I have shown you that an example with atom bouncing on the mirror, but you can consider, for example, electron moving in an atom, which is perturbed by the fluctuating microwave field, and then again, this phenomenon can be observed. And it is even possible to observe Anderson localized, delocalized transition in time. So, but this is an example of condensed matter phase in the time domain, but this is a single particle problem. But actually what we can do, this is period of the resonant orbit. So if you go, let's say, later in time, then you see a repetition of this one, because you have a periodic boundary conditions in time. Like in a space crystals when we are going again and again along the ring. But actually we can drive also resonantly many-body system, for example, ultra-cold atoms bouncing on the mirror. Then our time-binding description goes to the Hubbard or Bose-Hubbard Hamiltonian, depending on what atoms we deal with. And then we have additional terms which describes interactions between atoms. Originally, interactions between atoms are contact interactions, but surprisingly, these contact interactions can lead to even to long-range interaction in our crystalline structure. But usually, on-site interactions are dominated. So let's assume that these interactions are repulsive, and of course, we know that this system can reveal mode insulator phase. This is just a standard mode insulator. The sketch of the mode insulator phase in space. But again, when we switch to our system, then when we fix a position in space, then we observe that in locate detector, then we observe that in this mode insulator phase, we observe that the well-defined number of atoms are coming to our detector. There is no fluctuation in the number of atoms. There is no phase coherence between them because we basically realize mod in the delta phase. Here, of course, the larger the system in time domain you want, the larger resonant number you need. It is all in for periodic boundary conditions, but also there is no problem to introduce open boundary conditions because that depends how you drive the system. If you drive the system in such a way that the effective Hamiltonian is, let's say, Anderson Hamiltonian plus additional barrier, then effectively you can realize, you can cut the ring. And then of course this ring appear again and again, but basically you don't need to deal with periodic boundary conditions. You can have open boundary conditions, which is nice when you want to, for example, realize topological phases in time. Then this open boundary conditions allows you to introduce edges. Now, this is all one-dimensional crystalline structure in time, and of course it is hard to imagine multi-dimensional time crystals, but it turns out that the time lattices with properties of two-dimensional or three-dimensional system can be realized when we switch from the single mirror to two orthogonal mirrors, which oscillates in time, and we consider resonant motion of atoms between these two mirrors, then the system can be mapped to the two-dimensional Hubbard or Bose-Hubbard Hamiltonian, and two-dimensional condensed matter phenomena can be investigated. We can also combine time and space crystalline structure together. For example, if we consider a particle or atoms moving in a periodic potential in space, which is in the ultra-cold atom is a standard situation experiment. There is a optical standing waves creates such a potential for ultra-cold atoms. And now assume that we start shaking this periodic potential in space, periodically in time, and fulfill resonant conditions with atoms moving in each well of this periodic potential. For example, when we realize 3-to-1 resonance, then in each side of this potential, we create 3 resonant wave packets which are moving along the resonant orbit. And this system can be mapped to two-dimensional time-space lattice when we have special index which labels which sides we consider in space. But we have also temporal index which labels the choice of different states in this different wave packets on this resonant orbit. And of course, this is 1D, but we can generalize to the 3D, and then having 3D, then we can go to up to 6-dimensional time-space lattice, and actually we have shown that one can realize 6-dimensional quantum Hall. I don't have time to mention more, let's say, phases which you can realize in the time domain. Just let me sum up. I show you that Anderson localization in time is possible, mod insulator. If we have interactions and disorder, then we can also realize systems which reveal many-body localization induced by the temporal disorder. Topological time crystals, this is multi-dimensional time lattice, time-space lattices. One can also engineer effective interactions between in the, let's say, crystalline structure. Despite the fact that ultra-cold atoms are interact only via contact interactions, one can realize actually any kind of long-range interaction, very exotic long-range interaction in a time lattice. And also one can, let's say, try to invent some new objects. And I don't have time to tell you, but there is something like Anderson or topological molecules which can be realized by means of the proper driving in time, actually the interaction strengths between atoms. But these all are, let's say, systems which, or crystalline structure which are created by hand. Similarly, like in a photonic crystals. In photonic crystals, of course, we have we have a medium where the fabricated in such a way that the refractive index changes in a periodic way in space. And this is some analogous situation. So far, I have told you that everything was revealed crystalline structure, but was created by hand. But of course, we know that in condensed matter, solid state crystals emerge spontaneously due to the self-organization of the many-body system. Not really, no. Because let's say the domain where we observe crystalline structure is a time domain. So this is not the frequency domain. Yes, but if you want to have, for example, if you want to have the system which is described by the condensed matter model, then in our case, this condensed matter model actually can be realized when you consider time as a degree of freedom. Spontaneous formation of, now let me also tell you that it is possible to spontaneously, to realize spontaneous formation of time crystals. Some short, brief history of this research. Everything started in 2012 when Frank Wilczek published his paper on quantum time crystal. But of course, we know that his idea was basically not correct, doesn't work. And then there was a hunting for time crystals. In 2015, there was a first proposal of something what we call today discrete time crystals. It was in atomic systems. A year later, the same phenomenon was proposed in spin systems. And the next year, there was the first experiment, and this field actually became quite attractive at that time. Okay, so, but before I explain you the formation of time crystals, let me start with something which is more familiar to everybody, the formation of space crystals. Suppose that we have solid state system. If we have a solid state system, the solid state Hamiltonian, of course, doesn't change when we translate all particles by the same arbitrary vector. And this is because interactions between electrons and nuclei depends only on the relative distance between particles. So when we shift all particles by the same arbitrary vector, the Hamiltonian doesn't change. And of course, then this is symmetry of the system, and symmetry in quantum mechanics is important. So from this symmetry, one can easily get the conclusion that if we calculate the single particle probability density, the probability for the detection of a single electron or a single nucleus, this probability has to be uniform in space if the system is prepared in an eigenstate. So where is the question? Where are the space crystals? But of course, we know that space crystals emerge due to the spontaneous breaking of this continuous space translational symmetry into the discrete space translational symmetry. And this is due to the fact that the ground state of the solid state system is strongly vulnerable to any perturbation. It is sufficient, symmetric ground state. It is sufficient to measure the position of only one atom, the system, and then the probability for the detection of the second atom starts revealing periodic behavior in space. This is somehow that the interacting system tries to self-organize with a regular distribution of atoms, but there is a symmetry. And one can naively think that the truth symmetric ground state is a somehow continuous superposition of space crystals. The measurement localizes the center of mass, and then we have space crystals. This is just some naive picture. Okay, so that's space crystals. But now let us switch to time crystals. If we have a time-independent Hamiltonian, eigenstates of the time-independent Hamiltonian are also eigenstates of the time translation operator, because this is evolution operator. And then again, from this symmetry, we can get the conclusion that if we fixed the position in space, and if we ask how the probability for the detection of the single particle or a few particles at this fixed point, how it changes in time, it has to be constant in time if the system is prepared in an eigenstate. Of course, this is trivial conclusion because we know that eigenstates of the time-independent Hamiltonian are stationary states. However, in 2012, Frank Wilczek proposed a many-body system which even if it was prepared in the ground state, it was expected to break spontaneously continuous time translational symmetry into the discrete time translational symmetry. In other words, the system was expected to switch to periodic motion spontaneously. And that, of course, it turns out that it was not possible. I'm not going to talk about these problems. I'm going to talk about systems which from the very beginning are periodically driven. If the system is periodically driven, the energy is not conserved, but still we can look for a kind of stationary states, which are called Floquet states, and which are eigenstates of the Floquet Hamiltonian. This is a different notion. In atomic physics, usually this operator is often called as a Floquet Hamiltonian. This is nearly energy, but this is supplemented with the differential operator. Eigenvalues of this Floquet Hamiltonian are called quasi-energies of the system, and these are in full analogy to the somehow semi-classical approximation to the Dresden atom picture in atomic physics. Anyway, all Floquet states must be periodic with the period of the Hamiltonian because this is a discrete time translational symmetry of the system. But I will show you that there are systems which can spontaneously break this symmetry, and the system can spontaneously start evolving with the period different than the period dictated by the drive. Okay, so let us consider this proposal of discrete time crystal in atomic system. Suppose that again we have ultra cold atoms which are bouncing on the mirror. They are bosons. And let us focus on the 2-to-1 resonance. If the interactions between bosons are very weak, then nothing special happens. And when we ask for Floquet state of the system, then they are very simple because this is each atom is in the superposition of two localized wave packets moving along the resonant orbit. However, when the interactions between atoms become sufficiently strong and attractive, then we observe quantum phase transition because we observe that at some point it is energetically favorable to group all atoms in a single localized wave packet. And then there are very special many-body Floquet states form. For example, when we have all atoms in one of the, all atoms in one of the wave packet and plus all atoms in the other wave packet. These Floquet states, of course, evolve with the period of the driving because it's a Floquet state. But this is, of course, Schrödinger-Kedlake state. So sufficient to measure one new position of one atom, and the system collapses to one of these two states, to which one, of course, depends on the result of measurement. Anyway, starting from this moment, the evolution takes place with the period twice longer than the driving period. New periodic motion spontaneously emerges. In other words, new crystalline structure in time is observed. And when we want to analyze the lifetime of this symmetry broken state, it is easy to do it within the basically rotating wave approximation. Then we get the conclusion that the lifetime increases exponentially with the increase of the number of parts of bosons. But of course, this is a rotating wave approximation, so this is not a strict proof of the stability. That was in 2015. A year later, two groups, but actually with this system, you can realize something what we call big discrete time crystals. Where we observe that once the symmetry is broken, then the system starts evolving with the period, for example, 100 times longer than the driving period. And this is actually experimentally, in experiments which are on the way, it will be easier to realize big discrete time crystal from some, let's say, suitable range of parameters. Okay, so that is, I don't have to actually tell you about discrete time crystal in spin system because Roderich explained it in details. I would like to only mention that in this system, still there is no rigorous proof that it is absolutely stable discrete time crystal. So the question is, can we, let's say, propose system where we can be sure that this is absolutely stable discrete time crystals? Actually, we can. let us modify our experiment with bosons bouncing on an oscillating mirror. And now let us consider bosons moving on a ring, which are resonantly driven by the potential which lattice potential, rotating lattice potential. This Hamiltonian possesses discrete time translational symmetry and also discrete space translational symmetry. And when we switch to the frame moving along the resonant orbit, basically to the moving frame, then we obtain that our Hamiltonian becomes time independent. This is exact time independent Hamiltonian. We didn't need to neglect any highly oscillating terms. And then we end up with a system of bosons in a double well potential. And then it is well known that bosons in a double well potential with attractive contact interactions, they reveal so-called self-trapping phenomenon, where they spontaneously break the symmetry of the double well potential and spontaneously localize in one of the potential well. This spontaneous breaking, this self-localization, when we go back to the laboratory frame, will correspond to the spontaneous breaking of the discrete time translational symmetry and to the emergence of the discrete time crystal. And there is no problem with stability of these discrete time crystal states because these states are actually mapped to the low energy eigenstate of the simple time independent problem. Let me illustrate this for a finite number of particles. This is the excitation spectrum of the Hamiltonian in the moving frame. So there are actually, in our case, there are three ranges of behavior depending on the interaction strengths. If we have a weak interaction strength, interactions or no interactions at all, then if we prepare all bosons in a single potential well, and we observe the system in the lab frame, then we see initially that the bosons evolve with the twice longer period than the driving period, but they gradually start tunneling to the other wave packet on the other side of the ring. And the time of the tunneling is basically given by the inverse of these gaps in the excitation spectrum. However, when we start increasing the interaction strengths, attractive interaction strength, then we see that there is a formation of doubly degenerate levels. And this is a signature that in the in the limit of infinite number of particles, we observe quantum phase transition, and we observe the formation of basically discrete time crystals. And the number of doubly degenerate states is extensive, is extensive, and this is up to the energy corresponding to the so-called symmetry broken edge. And okay, this is the second regime. But if we keep increasing the interaction strength, then we entered another regime, because we enter basically in cold atoms we called bright soliton regime. Because for strongly interacting system, then the character of the excitation, lower excitation spectrum changes, because in this discrete time crystal, simple discrete time crystal regime, the excitation spectrum corresponds to the quantum depletion of the Bose-Einstein condensate. So it has many-body character. However, in this strong interacting limit, then the system, the lowest excitation spectrum corresponds to the excitation of the center of mass of the soliton. So then in this regime, we are in the basically single body problem. Oh, I have, can we observe spontaneous formation, not only time crystal, but quasi-time crystal? So, okay, so what are quasi-crystals? Quasi-crystals are solid-state systems which lack translational symmetry, but still reveals long-range order. The simplest quasi-crystal is one-dimensional Fibonacci quasi-crystal, and Fibonacci sequence can be generated with the help of line whose gradient is given by the golden ratio. And successive cuts of the line with the vertical and horizontal axis of the square lattice generates Fibonacci sequence. And if we choose a line whose gradient is given by the rational approximation of the golden ratio, then we can generate a finite Fibonacci sequence. How long? It depends how good is the rational approximation. So that's the introduction, but now let us consider our physical system. Let us consider atoms which are bouncing between two orthogonal mirrors. This is one and the second. And both mirrors oscillate, but oscillates with the same period. It means that we have discrete time translational symmetry in the system. But now assume that we choose a resonant motion corresponding to Sx to one resonant condition with the left mirror and Sy resonant condition with the right mirror. And then if the system, there is no strong interactions, then nothing special happens because resonant Floquet states evolve periodically. And when we ask how the probability of hitting of the left and hitting of the right mirror, how they change in time, they change in an alternate way. However, when the interactions are sufficiently strong, then we can observe spontaneous symmetry breaking. And then when we ask how the probabilities of hitting left and right mirror, how they change in time, they form Fibonacci sequence. This is very short Fibonacci sequence because we have chosen very bad rational approximation of the golden ratio. But we can choose as good rational approximation as we need. And then when symmetry is, discrete time translational symmetry is broken, then we observe formation of Fibonacci sequence in time as long as we wish. So now let me conclude, which is also related to time tronics. I have told you that periodically, in a periodically driven systems, we can realize many different condensed metaphenomena which are observed in the time domain. Periodically driven system, we can also observe spontaneous processes, spontaneous formation of discrete time crystals. And as I already told you that it could be big discrete time crystals. It can be observed even fractional time crystals and quasi-crystals. So we have many different building blocks. Now I think this is a moment when we can try to invent some useful devices and try to build something where crystalline structure in time is play a crucial role. And this is research on the way, and we have a close collaboration with the experimental group of Peter Hannaford in Melbourne, who is doing setting experiment on ultra cold atom bouncing on the mirror. We have also collaboration with Hossein Taheri group, who is doing experiment in photonics. At the beginning, I have shown you a long list of people involved in the research. Let me show you what the results they produced, and there is also a book on time crystals. So, yes, thank you very much.
Questions?
I had a fundamental doubt about discrete time crystal. Like after the formation of time crystals spontaneously, what will happen to the oscillations if we stop the driving? Will it sustain or not?
If we stop the driving, at least in our case, what is happening, this is just, again, a simple, that corresponds to the simple problem with even a single particle bouncing on an oscillating mirror. If you have a static mirror and you prepare a localized wave packet, then this wave packet, initially it starts bouncing, but on longer time scale, even not longer time scale, after very short time, it also starts spreading. And this is very important that the driving leads to the refocusing after each bounces, leads to refocusing of this initially localized wave packet. So then only in the presence of the driving, you can define this, let's say, localized wave packet moving periodically along the resonant orbit. So I would say that even if you have interactions and this entire, let's say, picture is totally broken.
Okay, thank you.
Yeah.
Okay, so I was thinking you told about the structures which repeatedly comes back after time, which has the same amplitude. But if there are small fluctuations on top of it, how would I understand that?
But you mean that, for example, in case of, I don't know, Anderson localization or what?
No, just from the fundamental definition of the time crystal, there are same amplitude that is coming back periodically in time. If those amplitudes are fluctuating, but there is this spacing is already perfect, how would I understand it?
Okay, that if concerning this, the discrete time crystals, if you start with let's say, if you consider a certain Floquet state, and then you break the symmetry, then there is no, this is a purely periodic evolution. There is no fluctuation probably you have in mind. Of course, in real experiment, you don't have this kind of system. So you have, of course, on the top of it, you have some fluctuation because you are not able to prepare exactly this state, but it doesn't matter, provided that that you don't need any fine tuning. If you don't need any fine tuning, because you can change the parameters of the system, and the system is still robust to these changes. Of course, if you could prepare some additional contribution to this state, you will see this additional contribution. But sometimes discrete time crystals are a signature of discrete time crystals if a peak in the Fourier spectrum at the half frequency. So you will always see this peak, but or possibly also some other, let's say, small contribution.
Thank you.
More questions? So maybe I had a question about the slide on self-wrapping.
Self-wrapping, okay.
So even classical systems have this self-wrapping, right?
Okay.
So is there any, yeah.
Okay, this is good question, because one can ask, if I have a classical ball, and if I move twice faster, then I realize 2-to-1 resonance, and this motion is stable, no problem. So is it classic? It is a time crystal or not? Of course, it depends if you want to call it or not. But what is happening if we have the same classical problem, but now we switch to the quantum description? If we switch to the quantum description, then initially you observe this motion along the 2-to-1 resonant orbit, but then you see quantum tunneling. So, in a long time scale, there is no chance for periodic motion. What you have to do, you have to kill this tunneling. And you can kill it when you observe self-trapping phenomenon, because then, let's say the tunneling means that you have to, let's say, tunnel all atoms at once. And that takes, for infinite number of atoms, that takes forever. And that is why you observe this degenerate state, which is exactly correspond to this physical picture.
Thanks. Okay, so, if there are no other questions, let's thank the speaker and all the speakers of the session.